causes an object to move through a distance, we say that work is done.
You've never done a day's work in your life.
No, not that kind of work, you grubby little man.
You talk.
Energy is transferred when work is done. Work done can be calculated using this equation.
Work equals force times distance.
Work done is measured in joules.
Back of the net. Give us an example.
When a car brakes, work is done to transfer the car's kinetic energy into heat energy. When we lift something like this crane here, work is done against gravity. Kinetic energy is transferred into gravitational potential energy.
Alright, I get it. So when I drag a gate across the floor, work's been done against friction. Is that right?
Yeah, can I go out?
When's it come out? Good night, fair maidens, and the blokey chaps too.
So from that video there you can see that work is only done when a force moves an object from one point to another, and two factors here affect the work done. That is the force, magnitude of the force, and the distance traveled. If the force is not pointing in the direction of the distance, then the work done reduces in size. Let's check this out. From this we can see that the force's direction is 0 degrees to the horizontal. In other words, it's going in the direction of the force. But when alter the direction of the force to a different angle, you can see that this is moved is only half of this rectangle here. So magnitude of force together with its direction and the distance traveled affects the work done. Let's check the slides out for more illustrations. Alright, from that video that you've just watched there, we can appreciate that work and energy are interrelated. In other words, where there is work, there's always energy, and where there is energy, there's always work done. So let's try to look at work in details. So from what we've just discussed there in that video there, we can say that work is dependent on two factors. Number one is the force, and number two is the distance moved. Whenever defining work, we always pay much attention to the direction of the motion of the body. So in short, we define work as the product of force and distance moved in the direction of the force. In the direction of the force. This one is very important. And you can even try to recall about moments. They have the same equation, force times distance, but what separates them is the distance moved. In work done, it is direction in the direction of the force, and then in moment, it's the perpendicular distance. That's why we need to pay more attention to the direction. So from that, we can simply say that work is equal to force times distance moved in the direction of the force, and our equation is work done equals to the force times the distance. We're using the S to represent the displacement or the distance moved in the direction of the force. So one other thing that we need to note is that work is a scalar quantity, and a scalar quantity is that with only size. In other words, the one which is described in terms of the numbers, 10 kilometers, 4 meters, 4 joules, like that. So work is also a scalar quantity. Much as we're looking at the direction of motion of the body, it is a scalar quantity. Don't confuse it with vector quantities. Then it is also a derived physical quantity, meaning that it is got from the fundamental or from the basic quantities of length, time, and mass. So the SI unit of work is a joule. It is a capital J in case you're writing a symbol, and then a small j if you're writing the word joules. And also note that 1 joule is the same as 1 Newton meter. So how do you define a joule therefore? Since you remember what work is, get the joule from the definition of the work. In other words, a joule is defined as the amount of work done when a force of 1 Newton moves through a distance of 1 meter in the direction of the force. So another question that we need to ask ourselves about is the dimensions of work. You can pause the video and try this one out. Now that you've tried out, let's try to check whether what you've done is correct or wrong. So dimensions of a physical quantity. expressing that physical quantity in terms of the basic quantities of length, mass, and time. So the dimension of work is got as the dimension of the force times the dimension of the distance. Remember, the symbols are very important. They are we use those brackets there. So remember that force is equal to ma. M is the mass, that is a fundamental quantity, and then a is the acceleration. Acceleration is measured in meters per second squared. We're just getting a hint from there. So meters, that is length, second square, that is time, power -2. And then the distance is measured in L. So we can simply say therefore that the dimension of work is equal to the mass, capital M, times the length squared. We're multiplying this L times this L, and then times the T power -2. This is the dimension of work done. Remember, when we're showing the dimensions of work, we use these brackets here, but in the final expression, those brackets are not there. That is the dimension of work done. So we've just discussed that work done is equal to the force times the distance. Now, assuming that the distance is not going in the same direction as the force, what do we do there? That's where the idea of components come in. So you have to resolve either the force onto the direction of the S, or we have to resolve the S onto the direction of the F. Both of them must be in the same direction. In case you've forgotten, just a hint here, from right-angled triangles, if I have my angle theta here, and I have this is my opposite where the angle faces, this is my hypotenuse, and then this is my adjacent. I'll call this on my x, I'll call this on my y, and then this is just my y, my hypotenuse. So from cos of theta being equal to adjacent out of the hypotenuse, I'll simply come and say that my adjacent is equal to the hypotenuse times the cos of theta. In other words, anything which is going in the horizontal direction, I'm calling it the x, it will be equal to the hypotenuse, which is my f in that case there, times the cos of an angle, which is that cos theta there. In other words, if the angle is onto the x-axis, then always use cos. If the direction that you want to resolve to is in the horizontal, and the angle is on the horizontal, between the horizontal and then you always use the cos. So I can either have this one as my f times s cos of theta, because the angle is here, or I can have my f times the s cos of theta. So the choice is always yours. So from that expansion there, you can simply say that therefore that work done is equal to f s cos of theta, and the point of application of the force F moves the distance s cos of theta when the object moves through the distance s. In other words, in this case, we have resolved the displacement s. Alternatively, someone else may get the work done as equal to the F cos of theta. This time around, you resolve the force times the displacement s. It is all the same thing here. So that is what we have as work done in terms of calculations. Let's try to look at examples, but before I go to the examples, we can also have this note that the work can either be a positive or a negative. Negative work done can be, for example, done by forces that oppose motion. For example, the friction force. For example, the viscous drag. All those forces that try to retard motion give us a negative of the work done. And then the forward forces give us the positive work done. Okay, So let's have one example here. The question says that calculate the work done when a force of 5 kilonewtons moves through a distance of 30 centimeters. In this case, it is always better that you first of all highlight what has been given to you. So we have 5 kilonewtons and then 30 centimeters. And note that these are not the SI units of these respective quantities. And since we're going to get the work done in joules, then it is better that we also convert everything to their SI units. So from work done is equal to force times distance. Our 5 kilonewtons into newton is the same as 5,000. The word kilo means 1,000. Then 30 centimeters, changing it meters, we get 0.3 meters. So multiply those two, you'll get the answer as 1,500 joules. Someone else may say that it's same as 1.5 kilojoules. It is also very okay, no problem with that. So that is the first example. Example number 2 says that calculate the work done by a child of weight 300 newtons who climbs up a set of stairs consisting of 12 steps, each of height 20 centimeters. In this case, the work done is going to be done by the weight of the body, and the stairs are moving upwards like that. So since there are 12 of them, then our height h will be equal to the height of each stair, which is 20 centimeters, times the number of stairs, which is 12. And this will be equal to 240 centimeters, which is the same as 2.4 meters. And if you have to follow this, our work done is equal to force times distance, and the child must exert an upward force equal to its weight, meaning that the distance moved as well, we've just got that one as 2.4. So using those two, work done will be equal to the force, which is 300 times 2.4, which is the height. The answer will be equal to 720 joules. Now here what you need to note as well is that where the force points, in this case the force is pointing downwards, and that is the weight. The height that is moved or the distance moved is in the vertical plane as well. So those two are in the same plane, they're in the same direction. So that's why we simply multiply the two. And from this you can even tell that what we are calculating actually is what we call the gravitational potential energy. We shall look at that later on. Potential energy is equal to mgh. I know you have looked at this already, where the mg is the weight, it is acting downwards, and then the height is also vertical. So it is the same as the potential energy. Number 3, this one changes a little bit, whereby the direction of motion is different from the action of the force. So the question says that calculate the work done by the wind on the yacht in the situation shown below. So the distance moved by the yacht is 50 meters, that is the boat, and the wind is blowing in this direction. So in this case, what do we do? Like we've said earlier on, you begin by resolving. You either resolve the distance onto the direction of the force, or resolve the force onto the direction of the distance. So in this case, we know that our work done, from the definition of work done is equal to force times the distance. Our force is 800 newtons, and our distance is 50 meters, but in this direction. Yet the direction that we want is this. So what do? We resolve this to the horizontal. So it will be the cos of 30 degrees. Remember, if the angle is onto the direction that you want, then use cos. So in this case, we shall be having 50 times cos of 30, and therefore our answer is 34,641 joules. I hope that is okay with you. Okay, so after having looked at that, since we're getting the work done as force times distance, sometimes we may be given a graph, and in case we've been given this graph of force against displacement, the work done is always equal to the area under that graph. In this case here, number 1, we're having a rectangle, so work done will equal the same as force times the distance. In number 2, we're having a triangle. In this case, the work done will equal a half times the force times the distance. And then in number 3, the curve is non-linear. The graph is non-linear. So in this case, we have to integrate. You integrate with respect to the distance. So our work done will be equal to the integral from negative infinity to positive infinity of f times the displacement s. So we'll do this later on, but at the moment it is not part of what we are supposed to do. So the area under the curve is equal to the work done, and we shall still look at this under energy. I'll be reminding you. Okay. So number 3 or number 4, calculate the work done by the brakes of a car if the force exerted by the brakes varies over the car's braking distance of 100 meters as shown in the graph below. So in this case, maybe the car was moving at a constant force, driving force, and then when the brakes were applied, the car decelerated uniformly up to maybe this point here. So calculate the braking force in the first 100 meters. So you can either begin by having this one as a triangle, you get its area, then you add up the area of this rectangle. The choice is always yours. So the area under the graph is 125 joules, and that is the answer to our question. Please try out more questions in the exercise. Try them out, they're there, and we move on together.